Good morning, everybody. Welcome to the second day of the conference. Before we start with the scientific part, I have two short announcements. First of all, unfortunately, Professor Nikolai Makarov just informed us that he would not be able to come. He did make a very valiant effort to attend the conference, but due to reasons, weather, transport, etc., that are really not his fault, unfortunately, with great regret, he cancelled his attendance. Consequently, there will be some minor changes to the schedule pertaining to Saturday, the last day, tomorrow that is. Please check your webpage in due time, and changes will be made explicit. The second issue that I want to mention is that if you have not yet signed up for lunches today, please do so with Alexei. He will pass these sheets. So just check the menu, put your name, and please note that today there is fish offered on the menu. So now I would like to ask Professor Michał Wojciechowski from the Polish Academy of Sciences to chair this session. Thank you very much.
So welcome everybody. It's well after 10 o'clock. So we start the first morning session. Our first speaker will be Professor Javier Tolsa, who will talk about rectifiability, Risch transforms and harmonic measure.
First of all, thanks for the invitation to talk here. It's an honor to talk in this conference in honor of Sasha. I remember that when I was young, around the time I finished my PhD, I learned a lot of techniques and ideas from the papers of Sasha, Nazarov, and Trail about non-doubling measures, Tibet theorems, and so on, which were very useful for me. And then later I had the opportunity to collaborate with Sasha, and I think that we obtained very nice results. Some of them will be mentioned here. Okay, so happy birthday. And let's start. So I will talk about rectifiability and the connection with Risch transforms and harmonic measure. And these topics, I think they are very related to the research of Sasha. Right. So let's start with some definitions. So Hn in this talk stands for the n-dimensional Hausdorff measure. Most of the time we will be in our n+1, although this first slide talks about Rd. So a set E in Rd E is n-rectifiable if it is almost everywhere with respect to n-dimensional Hausdorff measure contained in a countable union of C1 or Lipschitz n-dimensional manifolds. It does not matter if we take Lipschitz or C1, because up to sets of zero measure we get the same. Also we say that a measure mu is n-alpha regular if there exists some constancy such that for all x in the support of mu and all radius up to the diameter of the support, the measure of each ball centered at x and radius r is comparable to the radius to the power n. And then we say that E is n-alpha regular if the n-dimensional Hausdorff measure on E is n-alpha regular. All right. And here comes the definition of uniform n-rectifiability. So if you are not familiar with this notion, just think that this is a quantitative version of rectifiability. Anyway, the precise definition is this one here. A measure mu is uniformly n-rectifiable if it is n-alpha regular. And moreover, there are two constants, n and theta, such that for all x in the support and radius up to the diameter of the support, there exists a Lipschitz map G from this n-dimensional ball in Rn to Rn+1. So because we are now in Rn+1, with Lipschitz constant bounded by m, and such that for this ball Bxr, a big portion of the measure is contained in the Lipschitz image of this ball, or big portion in terms of this constant theta. So in plain words, one says that the measure mu, or the support of mu, has big pieces of Lipschitz images. This is the usual terminology. And then a set E is uniformly M-rectifiable if the corresponding Hausdorff measure on E is uniformly N-rectifiable. So uniform N-rectifiability is a quantitative version of N-rectifiability, as I said. It is very easy to check that it implies rectifiability, and this was introduced by this notion by David and Sems in the early 90s, and to study this notion, they used some coefficients like the beta 2 coefficient that we will introduce here, and they obtained they obtained many interesting results and that connect uniform rectifiability to harmonic analysis. Anyway, before going to the beta coefficients, let's introduce first these theta coefficients. So for a ball BXR and N, this is contained in RD or in Rn plus 1, what you prefer. So the n-dimensional density of this, or average n-dimensional density of this ball, is the measure of the ball divided by the radius to the power n, and we denote by theta sub mu of xr, or theta sub mu of the ball. So notice that this thing depends on the power n. We are interested in n-dimensional densities because we will be interested in n-dimensional rectifiability in Rn plus 1. And then this beta mu coefficient is equal to this thing. So it's the infimum over all n planes of the square root of this quantity. So this is 1 over the radius to the power n, and we integrate in this ball, and here we take the distance from this n plane L, we divide by r square, and we integrate with respect to mu. All right, so this looks a little technical, but as I said, theta sub mu is a density coefficient, and beta sub mu 2 measures how close is the measure mu, or the support of mu if you want, to be concentrated close to some n plane L. So, and we measure this closeness in terms of this L2 norm. Notice that this is a scale invariant quantity, distance divided by r, and for instance, if the measure mu is n-alpha regular, essentially this coefficient is a scale invariant, right? Because we have, this is scale invariant, and then we have measure divided by r to the n. If the measure is not alpha regular, beta sub mu 2 scales like the density to the power 1/2, right? Because it's mu divided by Rn, so it's density power 1/2. This is the right scaling. All right, and here I have a picture of how you can think that we measure how close is a set E, or here is the support of mu to be close to some line L. So of course, if this coefficient is 0, then this means that the measure is mu in the ball is supported in some n plane. All right, so as I said, David and Sems studied uniform rectifiability. They introduced this notion, and they characterize uniform rectifiability in terms of some Carlson type condition involving the beta mu coefficients. But for the purposes of this lecture, for us it will be better to announce this result that was obtained some years later, about almost 20 years later, by Jonas and myself, that concerns general measures mu, not without the alpha regularity condition. So so imagine that we have a Borel measure mu that is supported on a ball B, and such that it has this growth condition. So here we are saying that the measure of any ball divided by the radius to the power n is uniformly bounded by this density of the larger ball. with time some constant. Then, if this square function involving these beta mu coefficients, so here we square this, we have integral, the usual thing, dr over r, and then we integrate with respect to mu, and we have this. If this is small enough, so because we assume this epsilon is small enough, and this, remember that I told you, beta mu scales like density to the power 1/2. So beta mu square scales like this density. So this is the right scaling for this quantity. So if this thing is small enough with the right scaling, then a big portion of the measure mu is supported in a uniformly n-rectifiable set. So here we don't assume this measure to be any kind of Hausdorff measure, for instance. But at the end, the smallness of these quantities, forces a big portion of the measure to be like Hausdorff measure, because this implies absolute continuity. Well, if on gamma, the measure, moreover, is absolutely continuous with respect to n-dimensional Hausdorff measure. This is just to check. And but also, almost the same theorem gives you that we can have the same result if we introduce, if we multiply this by the density here, and here we put another power 2. Just maybe you. It's not. This is not just a curiosity. What happens is that this will be useful because this will have connections and applications for these transforms. All right. This is what I said. On gamma, the measure mu is absolutely continuous with respect to n-dimensional Hausdorff measure. Let me say that after this result was obtained, then other results or related results of similar quantitative nature were obtained by Edelin, Neighbor, and Baltort, and they applied these results to the study of some singular sets for free boundary problems. Also, Leger in the around the year 2000, so much earlier than the result, he obtained some similar result, but stated in terms of curvature of measures instead of beta mu coefficients. But we will not talk about curvature here. All right. So just remember that this square function involving beta mu coefficients, the smallness implies that a big portion of the measure is absolutely continuous with respect to Hausdorff measure and rectifiable. Now let's go to harmonic measure. So roughly speaking, harmonic measure is defined in this way. So we consider a set omega open in Rn plus 1, and then for a point P inside omega, the harmonic measure omega super P with this pole, with pole P in omega, is defined in this way. So for a set E in the boundary, contained in the boundary, its harmonic measure coincides, harmonic measure with pole at P coincides with the value of the harmonic extension of this characteristic function of E to omega evaluated at P. Of course, this is one has to be a little more careful when if we want to define this correctly, because of course it is not very clear what means harmonic extension for very general sets. But we can agree with this. Then, harmonic measure is a classical topic in analysis. This has connections with complex analysis, with PDEs, with the solution of the Dirichlet problem, and then some natural questions arise when one wants to understand the behavior of harmonic measure. For instance, when does harmonic measure is comparable or mutually absolutely continuous with respect to this n-dimensional Hausdorff measure? So we are in Rn plus 1, so for nice domains, you can think that this is like surface measure on the boundary. Which is the connection of harmonic measure with rectifiability, or what is the dimension of harmonic measure, for instance. So harmonic measure is defined in an analytic way, and then one wants to study the geometric and metric properties of harmonic measure. So and then to study these properties, an interesting tool is a useful tool is the Risk transform, so which is the third important notion on this talk. So for a measure mu, Borel measure mu in Rn+1, its n-dimensional Risk transform is defined in this way. So well, this is the Risk transform of mu, and this is the limit of the truncated Risk transforms, and the truncated Risk transform is this integral here. So we have this truncation, and this is the n-dimensional Risk kernel, and we integrate with respect to mu. And then, well, we will also consider the maximal Risk transform, which is the point was supremum of these truncations. Also, for a function, so we have to think that mu typically is a positive measure that is fixed, and then for a function f that is locally integral with respect to mu, one can consider the Risk transform operator, right, which is defined in this way. For a function f, the Risk transform of f with respect to mu is just the Risk transform of f times mu, and the same for the truncations. Then one says that the Risk transform is bounded in L to mu if the corresponding truncations are uniformly bounded in L to mu. All right, so this is the Risk transform. And then what is the connection, or why is it useful, the Risk transform, when studying harmonic measure? Well, for instance, because as most of you know, I think, the fundamental solution of the Laplacian in Rn+1 is given by this quantity here. So this is some constant times 1 over modulus of x to the power n minus 1. Well, in the plane there is a logarithm. And then, so the kernel of the Risk transform is just modulo some constant, the gradient of the fundamental solution of the Laplacian. So now you can guess then that the Risk transform maybe will have some connection or will be useful to study harmonic functions, right, for example. Well, then it turns out that the Green function for omega can be written in this way. So the Green function with xp, p, in all the talk, p, you have to think about p like this is the pole for harmonic measure, and typically this is a point deep inside omega. So the Green function essentially is like, or is like, or it behaves like the fundamental solution, but it has a correcting term here, so that when we do this subtraction, then this correcting term forces this quantity here to vanish when x is in the boundary of omega. So, in other words, the Green function is essentially like a fundamental solution such that it vanishes when x is in the boundary of omega. Then taking gradients, we have that the gradient with respect to x of the Green function, this is we get here the Risk kernel, we differentiate the integral, and here we get the Risk transform. So the gradient of the Green function equals the minus Risk transform of harmonic measure. And modulo some term that usually is not very problematic, because as I told you, you have to think that p is deep inside omega, and x, usually we are interested in points x that are very close to the boundary, or in the boundary, right? So then this quantity is uniformly bounded. So then we have that good properties for the Risk transform of harmonic measure are equivalent to having good properties for the gradient of the Green function, which in turn is equivalent to having good properties for harmonic measure, right? So this is the connection. Well, we had, as I described, the connection between the Risk transform and harmonic measure. Now let's talk about the connection of Risk transforms with rectifiability. So, and then, well, and here I announce a theorem that we obtained with Nazarov and Volberg in 2014, which asserts that if we have a set E in Rn+1 with finite n-dimensional Hausdorff measure, and we take mu equal to this Hausdorff measure, then the L2 boundedness of the Riesz transform with respect to mu implies the n-rectifiability of E. And when E is n-also regular, then it turns out that E must be uniformly n-rectifiable. In fact, in this second case, under this assumption, this is an if and only if. So L2 boundedness is equivalent to uniform n-rectifiability in the alpha regular case. Let me say that, well, this is the so-called solution of the David-Semmes problem, so we were very happy when we solved this. And, the case n equal 1 had been solved previously by David and Leger, this case, and the alpha regular case by Matila, Melikov, and Verdera. They used this, they did this using Menger curvature and the connection with the Cauchy kernel. Okay, area. All right, now I want to explain one application of this result, or the result and the connection between Riesz transforms and harmonic measure to what we call what was called or is called the two-phase problem for harmonic measure. This will be again a joint result with Sasha and other people. So in this two-phase problem, we have two domains, omega 1 and omega 2. Well, here for technical reasons, these domains look very smooth, but you have to think that typically the boundaries could be very rough. Right? And then we have a set E contained in the common boundary of omega 1 and omega 2. And well, we proved this result. So this is a joint result with Jonas Hassan, Michalis Morgoglu, and Sasha. And we showed that if we have these two domains that are disjoint, their boundaries intersect, and then we assume that the respective harmonic measures, omega 1 and omega 2, are absolutely continuous, mutually absolutely continuous, in some subset E of the common boundary, of this part of the common boundary. So this is the assumption. So harmonic measures mutually absolutely continuous on E. Well, then it turns out that on E we showed that harmonic measure must be concentrated in an n-rectifiable subset. And moreover, in this n-rectifiable subset, both harmonic measures are mutually absolutely continuous with respect to n-dimensional Hausdorff measure. So one of the big difficulties of this problem was, probably the most delicate point, was to show that that harmonic measure was concentrated in a set which had either finite Hausdorff measure or counter or sigma additive finite Hausdorff measure. Because here we are not assuming that the boundaries have finite surface measure. So these boundaries can have a dimension larger than n, for example. All right, some remarks, so, and we will say why this result also is connected to Riesz transforms. Well, this result had been previously proved by Bishop in the case n equal 1, that's this in the plane. Remember that we are in Rn+1. Also, without a thickness assumption on the boundary called the capacity density condition, that is weaker than alpha regularity. This has been previously proved by Jonas Hassan, Michalis Morgoglu, and myself. And then, well, this result had been previously conjectured by Bishop in the early 90s. So we solved this problem by Bishop. And what about the proof? Well, just I will not describe the main. Well, I just mentioned the main techniques of the proof without going into details, of course. Well, the proof uses a blow-up argument inspired by techniques introduced, well, or that introduced in this context at least, by Koenig-Presantoro. It uses the Alka-Ferrelli-Friedman monotonicity formula that is very well known in the field of free boundaries, but I will not announce it here. And it uses a rectifiability criterion in terms of Riesz transforms that I proved in collaboration with a student that I had, Hirela Sarrion. And this criterion for rectifiability is, the proof is inspired by the techniques of this prior theorem that I had with Nazarov and Bolberg. And I will not say in detail what says this criterion of rectifiability, and instead I describe in a rather rough way. So this criterion for rectifiability says that if we have a suitable ball with the beta coefficient small enough so that the measure is concentrated close to some end plane, and we assume that this L2 norm of the Riesz transform is small enough, because we assume this epsilon is small enough. And why do we put this density square here? Because this is the natural scaling for Riesz transforms. So we assume this quantity is small enough with the natural scaling. Then a big portion of the measure is concentrated in a uniformly n-rectifiable set. And now you can relate this result, so you should relate this result to the previous result that I mentioned that I had with Jonas Assam, where we saw that if we have some square function involving some beta mu coefficients small enough, then a big portion of the measure was concentrated in a uniformly n-rectifiable set. So it's the same, or an analogous result, but instead of involving a square function, here we deal with Riesz transforms. All right. So, and this was possibly the main ingredient to solve this two-phase problem. All right. And now I will describe some newer results. So, and first, and then to describe these newer results, I introduce these notions here. So we consider this maximal operator. So this is the maximal operator applied to mu. This is, with this n, is the supremum of the measure of this ball Bxr divided by r to the n. So it's just the supremum for a fixed point x of these densities. Of course, when we have an n-alpha regular measure, this is comparable to 1. And then we denote this upper n-dimensional limit, or this upper n-dimensional density. This is the lim sup of these densities as the radius goes to 0. We denote this by theta sum mu n, and then this upper asterisk. All right. Then in collaboration with Damian Dombrowski in 2023, we obtained the result that can be understood as a quantitative version of the theorem that I announced in collaboration with Sasha and Nazarov. And this asserts that if we have, these technical assumptions that this operator and this other operator, maximal operator applied to this measure, we assume that they are in L2 mu in this double ball. Then we assume that that this is a doubling ball. By a doubling ball, I mean a ball such that its measure is comparable to the measure of the double ball. Then it turns out that this square function involving the beta mu coefficients is bounded by the oscillation of the L2 oscillation of the Riesz transform, T oscillation, but written in this way. So here we integrate in B, and here we have the L2 norm square of on B of this Riesz transform minus the mean of the Riesz transform in the double ball. plus this density of the ball, power 2, times the measure, and plus this other term. So we here have the density of the larger ball B to the power 2, and here we have the density at the points. All right. An important thing is that this estimate applies to very general measures. That is, well, assuming these conditions here, it's much more. So these measures are much more general than are for regular. All right. Here I stated the same result again, and here, well, let me say that this result has applications to the pen-level problem for its harmonic functions that I will not. Well, but I will not enter into detail. Instead, here I put this question. So the question is if we have this estimate. That is, in this estimate here, is it true that can we eliminate these summands here? So this estimate here is true without these two terms, these summands on the right-hand side. And why is this interesting? Well, for instance, because if this estimate is true, under some assumptions, for example, then, and the risk transform is constant in the support of mu, then we would get that all beta coefficients are 0, and so the measure then must be concentrated in an n-plane. In fact, it is an open question to know if, even in the alpha-regular case, it is an open question to know if the vanishing of the risk transform of the measure in the BMO sense, does this imply that the measure is concentrated in an n-plane? This is an open question. All right. And then, the first result that I will present here is a quite partial or very partial answer to this question. In fact, we'll see that essentially, under some assumptions, we can eliminate this summand here, the first one. For the moment, I don't know about the second one. And we will see, okay, this, maybe you can think that this is just a technical result, but this has applications to the study of harmonic measure, and we will see this later. All right, so the precise result is this one. Yeah, in order to eliminate this quantity here, what I show is that this quantity here is in fact bounded by this plus this. This is what we show. So this quantity, I repeat, is bounded by the other two terms, but under some assumptions. So, and the assumptions are this one. So we consider a measure mu in Rn plus 1 with this condition here. We consider a doubling ball, and the key assumption is that there exists just a ball B1 centered in B such that its density is not too small, and such that its radius, we ask the radius to be quite small enough. So in other words, we don't want the density of the measure to degenerate and to go to 0 too fast. This is what we ask. So if this ball B1 exists, then with this delta number small enough, depending on this alpha, then we have that this term is bounded by the other two summands that I told you. All right? Okay. And as a consequence, well, we have what I told you, that this beta square function is bounded by the other two terms, with the implicit constant depending on these numbers. All right. So some remarks. First, what about this condition? Is it a natural condition or not? All right. So if we have a measure that is concentrated close to some n-plane, it is easy to check that there exists then some little ball whose diameter can be more or less close to the strip around which the measure is concentrated, such that its density is large enough. We just have to count the number of balls, and then we find a ball with a maximal density. So this condition implies the existence of this ball. But this is not very new, because we already had a result saying that if the beta mu coefficient was small plus other technical conditions, we had good estimates for this tensor. But the interesting thing is that this estimate typically holds for harmonic measure. Why? Because remember, we can consider a ball B, and then we want to find another ball B1 such as this one. Then imagine that we have a domain omega, and then we have a harmonic measure here, and then it turns out that by touching point arguments, if we consider, if we are close to some, if we draw, let's say, if we draw a circle such as this one, in this kind of points where we have these inner vertices, harmonic measure, the density of harmonic measure does not go to 0. In fact, in this drawing, the densities here explode. So there are many points where the density does not degenerate. And then for any ball, and at least under the capacity density condition, this can be shown. That for any ball B, another ball B1 satisfying this, with alpha, where alpha is just an absolute constant, well, maybe absolute, but depending on the capacity density condition, then by this argument, geometric arguments, one can show that close to these points, where a ball, in this case, a ball B1 just would be, we would take for ball B1 a ball centered at X with radius small enough. And this would be sufficient. All right. Well, combining the previous result with my result with Jonas, then we obtain this version of stronger version of the rectifiability criterion that I more or less described in collaboration with Hirela Sarion. This criterion for rectifiability says that if we have a doubling ball, so this is doubling, satisfying some growth conditions, with the measure on the ball satisfying some growth conditions, and with this key assumption about the non-degeneracy of density in some little ball, then if this oscillation of the L2 norm-Navier transform is small in the right scaling, then a big piece of the measure in this ball B is concentrated in a uniformly M rectifiable set. All right. About the idea of maybe we will come later about the idea of the proof of the theorem. Let me describe first the application to harmonic measure. All right. So we say that a function f from 0 infinity to 0 infinity is almost increasing near 0 if if there exists some fixed constant c such that for some r0 small enough, if we have two s and r positive smaller than r0, we have well, instead of assuming f of s is smaller than f of r, we assume f of s is smaller than f of r times some constant, right? Well, it turns out that, well, in a joint result with a student, Luis Lloret, we have shown that if we have an open set, omega, and with harmonic measure little omega, and then we consider here the set of where the harmonic measure has zero density. In the plane, this set has zero harmonic measure, because in the plane we know that harmonic measure is concentrated in sets of sigma finite length by a well-known result of Wolf. But in higher dimensions, we don't know if there are sets where this where there are domains omega where the set Z can have positive harmonic measure by deep examples of Wolf again. Well, then an important question is the understanding of these sets where the harmonic measure has zero density. Maybe this, well, this is a question connected to the dimension of harmonic measure. A very difficult question. Well, what we have shown is that in these sets, harmonic measure is not almost increasing at almost all points. So this property does not hold for the density of harmonic measure at almost all points. Or in other words, the density, it's true that it goes to zero, but remember, this is the upper limit of the densities of the harmonic measure in the balls, and we take the limit as the radius goes to zero. So this goes to zero, but what we are saying is that it oscillates. It goes to zero, but oscillating. Or in other words, we have that the lim sup, and then here of these quotients, and here we take this supremum, is equal to infinite. All right. So we have bigger knowledge, or a larger, we have increased our knowledge of harmonic measure. And an interesting remark is that this has an application, or this has an interesting connection, again, with the two-phase problem for harmonic measure. Why? Remember, in the two-phase problem for harmonic measure, we have two domains, omega 1 and omega 2, and we have a set E where the two harmonic measures are mutually absolutely continuous. Well, it turns out that in this set E, where both harmonic measures are mutually absolutely continuous, one can show, using the Alcafarelli-Freeman formula, that these densities are almost increasing for a radius small enough at almost all points. So we have a new proof of the two-phase problem, right? Because in the previous result, we said at almost all points with zero density, the density of harmonic measure is not almost increasing. So then what we're saying is that this set E, in this set E, the points of zero density have vanishing harmonic measure. And this is the main difficulty in the solution of the two-phase problem. All right. And now in the remaining minutes, a main idea of how do we prove this? All right. This is here again the same result. Well, very roughly, we consider a density point where this is finite, and then when we have a density point where this is finite, in a sense we have that the measure has some polynomial growth at many points in this ball. So we are then under the assumptions of that theorem here, that we require this. So, okay, so we are when we are in the assumptions, by touching point arguments, that the ones I described, we have that this ball B1 exists, at least in domains that satisfy the capacity density condition. This is easy. Otherwise, that's much more delicate, but this can be proven. And then we get that we have this estimate. But when we have this estimate, it turns out that in points of zero density, this is zero. And it turns out that the Riesz transform, essentially, it is equal to the, as a principal value, essentially it is equal to the n-dimensional upper density of Riesz transform. So both terms vanish, essentially, if at points of zero density. And then we get a contradiction because this is not zero, right? And well, so and just very quickly, remember, very quickly, how do we prove this theorem? How do we prove this theorem? Very quickly, remember that we have a measure satisfying this. This thing does not degenerate too much, and then this is what we want to prove. All right, very quickly. This is what we show. And then the argument is inspired. It follows more or less the same techniques or related techniques to the ones that we applied in the theorem that I have with Sasha and Nazarov. It's approved by contradiction. We assume that this is small. That is, it's approved by. We assume that this is small for some lambda very small. Then we consider this functional. That is this thing here. So it's this. We assume that this is. If this is small, then this function applied to some function L, A equal 1. This is very small. So that is when A is equal to 1, this quantity is the same as this one here. And this thing here, if lambda is small, this is very small. Then we minimize this functional over all functions L infinity, and then we get a contradiction using a suitable maximum principle. So of course this is like waving hands, but, and then where is used this assumption here in the maximum principle? Because this, in that argument there, one has to transfer some L infinity estimate from the support of mu to the ambient space. And then this thing here allows to use good estimates involving harmonic measure. And then one can transfer smallness from the support to a smallness to the ambient space. This is very, very roughly how this goes. All right, and that's all. Thank you.
Thank you. Now we have time for question, comments. Do we have some?
So excellent talk, thank you. I just wanted to ask you about these beta numbers which are related to a measure. So there are these beta numbers of Peter Jones which kind of give a solution of this analyst traveling salesman problem. Is there anything like that known for higher dimensional case, like for n equal to 2, for example? Do you have?
Yes. Yes. It's in the alpha regular case. In the alpha regular case, of course, then this is the Witten sense. This implies, but this is instead of beta infinity, one has to argue with beta p coefficients. For instance, beta 2 mu with T2 works always. One cannot use beta infinity because the beta infinity coefficients of Peter Jones, they do not satisfy a Carlson packing condition in higher dimensions in set that are rectifiable. Instead, the natural thing is to work with beta mu p, typically with p equal 2. And then here, there are, that is, in the alpha regular case, one has that if one asks this to be true, of course, in the alpha regular case, this is equal, this density is equal to 1, comparable to 1. If one asks this condition to hold for all balls B, then this is equivalent to uniform n rectifiability. But then also there are some quantitative results of this nature but usually by Edel and Neighbor-Martort and by others, but usually they say that if this is small enough, then some big piece of the measure is concentrated in some rectifiable set. There are other results with involve, I think, by Jonas Hassam and Ranan Schul, I think that involving beta, I think it's beta mu, I'm not sure, but beta coefficient with respect to Hausdorff's content, and they obtain some related things. That is the result of Peter Jones in higher dimensions does not hold in such a nice way, but there are suitable quantitative variants. Yeah.
Thank you.
Okay, do we have more questions?
Xavier, in this new result of two-phase, this Laureate also the technique, can it be like also given another proof of one-phase problem?
I don't think so, because the one phase problem is it's easier, right? And then here, in fact, of course, when I say we get a new proof of the two phase, what we have is a new proof of one of the ingredients of the two phase. Of course, when we prove rectifiability, then we use again the one phase problem. So that the main idea here is that, or the main remark here is that in the two phase, that these points with vanishing density do not exist, and what is interesting is that in points where one has mutual absolute continuity of the two harmonic measures, the harmonic measure is the density is essentially decreasing. But yeah, in the one phase, I don't know if one can get something newer. Yeah.
More questions? So, if no, let's thank the speaker again.
Thank you.
And the next talk begins at 11:30. Okay, after the coffee break, we restart our morning session, and the speaker is Professor Eva Gallardo. She will talk about quasi-triangular operators, compact perturbation of self-adjoint, or more general normal operators, and the Lomonosov theorem.
Okay, thank you very much. I would like to thank the organizers for their kind invitation. And okay, happy birthday, Sasha. This is not related to the work with Sasha in a direct way, let's say, but it is still related to the first block that Nikolai told us yesterday in some sense. So I hope that I will try to make some connections, and I try to convince you at some point that there are some singular integrals here in this guys. But probably I am in the operator theory side of the conference, and the starting point for my lecture is one of the most intriguing open questions in operator theory in Hilbert spaces, and this is the invariant subspace problem. The invariant subspace problem asks if there exists a linear bounded operator in a Hilbert space without non-trivial closed invariant subspaces. The Hilbert spaces we're going to consider are complex Hilbert spaces, and the trivial invariant subspaces are always the zero and the total, of course, and we ask if there exists a linear bounded operator without non-trivial closed invariant subspaces. Of course, there are a couple of remarks, quite easy. The first thing is that if we're considering just finite dimensional Hilbert spaces, complex Hilbert spaces, every linear operator has invariant subspaces, so there is no interest really in that. But if we consider non-separable Hilbert spaces, the answer is also positive. Every linear bounded operator has non-trivial closed invariant subspaces. And why is that? Because I take a vector in the space, a non-zero vector, I take the orbit, and the linear span of the orbit. If I close it, this is a non-zero space. This is not also the total space because it is separable, and it's, of course, invariant and closed. So the problem, really, it's open in the context of infinite dimensional separable Hilbert spaces. And despite all the announcements, this is remaining open. The origins of the problem are not pretty clear. Many people trace back to von Neumann, because he was he was the first who proved that compact operator has non-trivial closed invariant subspaces, but probably the intrinsic difficulty in order to understand this problem is, in words of Halmos, is that we don't know too many classes of operator that we do understand from the standpoint of invariant subspaces. And this is a real problem. Of course, we know classes of operator that they do have invariant subspaces. The first big class are normal operators, and this is just a consequence of the spectral theorem for normal operator. This is easy, those operators that commutes with the adjoint. The compact operators, the spectrum tells us that either it has eigenvalues or it is quasi-nilpotent. The spectrum reduced to the quasi-nilpotent case, and that was proved by von Neumann that compact operators has non-trivial closed invariant subspaces, as I said, and the general case in Banach spaces was proved by Anonson and Smith, and I will come back to this later. After that, there was a sort of, many authors tried to understand classes of operators that had invariant subspaces. The polynomially compact operators, that means that there exists a polynomial such that P of t is compact. The first result was due to Bernstein and Robinson in the Hilbert space setting, Halmos translated to the functional analysis setting, and many authors contributed to understand classes of operators that had invariant subspaces. Of course, there are not many names here, but clearly there are the subnormal operator that was a big issue, was Scott Brown, Chevreau, Piercy, many. In 1973, there was a breakthrough in some sense, and that was due to Lomonosov, who proved that those operators that commutes with a compact operator, which is not the zero operator, of course, has non-trivial closed invariant subspaces. Indeed, he proved much more. He proved that every operator that commutes with a compact one, a non-zero compact one, otherwise I'm not saying anything, has non-trivial hyper-invariant subspace. That means that it has a subspace that is invariant under every operator in the commutant of T. So for some time, people were trying to understand if every operator had a compact operator in the bicommutant, a non-zero, of course, compact operator in the bicommutant, because that would solve the invariant subspace problem. But unfortunately, this is not the case, or at least not from this perspective. It took a while to prove that not every operator has a non-zero compact operator in the bicommutant. That was proved by Hadwin, Norgren, Rajavi, and Rosenthal in the 80s. And they showed that there was a quasi-analytic chief in a weighted L2. Indeed, this is quite related to the chief operator, which is the best operator we understand in some sense. In the Dirichlet space, I won't go for details here, but the only compact operator in the bicommutant of such a quasi-analytic chief is the zero operator, so not an interesting one. What happens in the Banach space setting? Okay, in the Banach space setting, in 1975, Enflo made a very striking announcement in the Seminar Maurice Bars in Paris. He stated that there exists a Banach space, complex Banach space, infinite dimensional, separable, and an operator says that it is injective, it has dense range, and it has no non-trivial closed invariant subspace. It must be injective, otherwise the kernel is invariant subspace, and it must have dense range, otherwise the closure of the range is invariant. So those two things are there, but the announcement at the proof took more than 12 years to get it right and published. And in the meantime, Chasrid provided an example of an operator in the classical L1 such that it has no non-trivial closed invariant subspace. From my humble perspective, this is the first example of a linear bounded operator in the Banach space setting without non-trivial closed invariant subspace of a classical Banach space, because the one provided by Enflo was a constructive way. The norm was defined recursively. Here, this is very nice piece of work. Unfortunately, Chasrid passed away, but there is something that maybe it was not so remarked about Chasrid's example. It has no non-trivial closed invariant subspaces, but T squared has, and TQ. And actually, there was a question that if it is possible to construct in L1, an operator says that no polynomial in T has non-trivial closed invariant subspace. And after some while, we got it. I mean, we provided a counterexample in that sense. We provided a sample of an operator in L1 such that no polynomial in T has non-trivial closed invariant subspaces. Actually, no analytic function f of T. Of course, T in that case must be quasi-nilpotent in order to define a non-constant analytic function of T by the functional calculus. More recently, with a postdoc, we were able to provide even a linear bounded operator in L1 such that T squared has infinitely many invariant subspaces, but if I perturb it, T minus lambda I squared, for lambda different from 0, it has no one. So this is, L1 is quite complicated in some sense, and it provides us some structure. It comes from the geometry structure, indeed, of the Banach space that allows us to provide this sort of counterexample. Anyway, so what is the current status? In the Banach spaces, all the examples that we know by now are provided in non-reflexive Banach spaces. Even we don't know if it is possible to provide a counterexample in James spaces. For those of you who knows a little bit about Banach spaces, theory or Banach space theory, those spaces are contained in their bidual with finite codimension. We don't know if there exists a counterexample in those spaces, but the general question by now is open in all reflexive Banach spaces and in particular in Hilbert spaces. So this is the status of the problem, and clearly that was this is our main motivation in order to understand classes of operators, and that was some sort of recall for this audience. So let me start from where the real work we will talk about starts. And it starts from the idea of Halmos in order to generalize Aron-Sans and Smith theorem. Aron-Sans and Smith proved that in Banach spaces, I think it was the von Neumann result, that in Banach spaces every compact operator has non-trivial closed invariant subspaces. So what Halmos did was introducing the concept of quasi-triangular operator. What is a quasi-triangular operator? So we say that an operator is quasi-triangular if there exists a sequence of orthogonal projections, PM, converging strongly in the strong operator topology to the identity, such that TPM minus PN TPN, I don't know if it here, goes to 0 in no. What does this mean? Okay, this basically, if T has an invariant subspace, if I take the orthogonal projection onto that invariant subspace, what we have is that TP is equal to PTP. This is just having one invariant. So what this means is a generalization of that, and in some sense, that tells you that this operator, the quasi-triangular operator, of course, generalized the triangular one, but has a sequence of approximately invariant finite dimensional subspaces because the PNs are finite rank projections. Okay, and this is what Aron-Sans and Smith prove in their theorem. I mean, for compact operators, they restrict it to finite dimensional spaces. We know we do have invariant subspaces, and then we increase the dimension. And the compactness help us, the compactness help us in order to construct invariant subspace. So that was the main idea before this definition. And of course, when we give a definition, right, we have examples and counterexamples, right? Compact operators are quasi-triangular. Normal operators are quasi-triangular. Compact perturbations of normal operator are quasi-triangulars. What is not quasi-triangular? The chief operator. This is a wonderful, there is a very remarkable book by Nikolai Nikolsky, Treatise of the Chief. Everybody says that if you know the chief, you know everything. In some sense, that's true. This is not quasi-triangular operator. The chief operator, the standard chief operator, and we know even its invariant subspaces by Berlin theorem. All right. For some time, their goal was trying to prove that quasi-triangular operators, since they look like triangular ones, had invariant subspaces. But surprisingly, the results just go in the opposite direction. Apostol, Foyas, and Voculescu, and independently Ron Douglas and Carl Piercy, prove that if you have a non-quasi-triangular operator, then it has invariant subspaces, non-trivial closed invariant subspaces. So clearly the goal is just trying to understand what happens with these quasi-triangular operators. If we know how to construct invariant subspaces for that class, we solve the invariant subspace problem in particular. So that was the main goal, trying to understand subclasses of quasi-triangular operators. And I told you, the compact we know, the normal we know. What happens with compact perturbation of normal operators? What happens if I have n plus k, where n is normal and k is compact? Can we say something? Okay, I, of course, try to present you this from this subject from the perspective of invariant subspaces, but this is a very old problem from the former Soviet Union, and there was a large literature, and probably there are many experts here in that sense, in order to understand what happens with compact perturbations of Hermitian operators. For instance, if you have a Hermitian operator and you perturb it by a Chatten class operator, CP, there are results from the 60s from, Brodsky, Lissig, Goldberg, Kreim, Makaev. But by now, we don't know if every compact perturbation of a Cepheid joint operator has a non-trivial closed invariant subspace. We don't know this. And it's even a little bit surprising, but okay, if you have a Cepheid joint operator, you know where the spectrum is contained. It's contained in the real line. If we assume that the spectrum of the normal operator is contained in a C2 curve, later on we will see that this can be removed, but if it is contained in a C2 curve, Kitano proved that if you make a Chatten class perturbation of that operator, then it has invariant subspaces. But if it was not the case, if the spectrum of the normal operator is contained in any set, it's not known what happens for any compact perturbation of that operator in terms of invariant subspaces. Actually, the situation is even worse. What is the easiest normal operator you can think about? If I am with my PhD student or with my student, the easiest normal operator is just a diagonal operator. I take lambda n's, for instance, in the picture that Tolsa gave us, the snowflake, and I take a dense set of point there, and I put it in a diagonal, and I make a rank 1 perturbation of that diagonal operator. We don't know if they do have invariant subspaces, unless we have extra condition on the growth of the coefficients of U and B. And this is what I'm going to tell you. Okay, this is what I was working last few years with some of my PhD students and postdocs, but let me go through it, and there are some singular integral in these guys, in the proof. I think I have not a blackboard, but anyway, let me go step by step. And of course, there are many there have been many results, partial results, trying to understand these conditions by Rajalavipur, Rosenthal, Peter Rosenthal, Bernard Chevreau, Isabel Chalender, and more recently by Mihai Putinar and Dmitry Jakubovich, in order to understand how the spectrum is going to be in these cases. But the goals for today are basically two. The first one is trying to understand what happens with finite rank perturbation of a diagonal operator, even Chatten class, and I will tell you something about that. And this is what we call the Peirce theorem. And the second one is trying to understand what happens for any compact perturbation of a Cepheid joint operator. Those are the two goals I want to discuss or to show you today. So let's go for the first one. In the first one, somehow I have just a diagonal operator, and I make a rank 1 or finite rank perturbation. And in addition, if time permitted, and I will tell you, I will try to provide even a lattice description in those cases that we are able to say something about the existence of invariant subspaces. And this is probably pretty ambitious, but a lattice description in terms of what happens with normal operators. For normal operator, we have a wonderful functional calculus. It's a Borelian functional calculus. It provides lots of invariant subspaces, and that would be my goal at some point. But let us start with the finite rank case. And this is the context. So I don't have a blackboard, but the context is I take a diagonal operator. So imagine you have your favorite compass subset of the plane, of course not empty, and you take a dense set there. Those are going to be the lambda n's that I put in a diagonal, and I make a rank 1 perturbation of that diagonal operator. And despite this simplicity, what happens is that every rank 1 perturbation of a normal operator whose eigenvector span the Hilbert space is similar to this case. So in that case, this is like our model to analyze, and we prove that they do have invariant subspaces. We prove for all those whose eigenvector span the space. Okay, and here there is a first result, which was a sort of breakthrough from my perspective, because there is no condition on where the lambda m's are taken. You take any bounded sequence, of course, because you want a bounded operator, lambda m, and then you take in the diagonal and you make a rank 1 perturbation, u and b, and the coefficients of u, I'm going to call it for simplicity alpha n, those are the Fourier coefficients of u, and the coefficients of b are b times, okay? If you have the growth condition for u, for the coefficients 2 to 2/3 for each of them, then that operator has non-trivial closed hyperinvariant subspaces. So let me make a very naive picture in order to understand the theorem. I'm not assuming anything about the diagonal operator, right? So I'm taking alpha n, of course, this is the Fourier coefficient, they belong to L2. And this is the beta n, belongs to L2, so they belong to this basically square. So what the Foyas, Janko, and Pearcey proved is that if they belong to this blue square, then the operator T, this is a very nice picture, but I think it can be understood in this way. T, the operator has non-trivial closed hyperinvariant subspace. That means an invariant subspace which is invariant under every operator that commutes with it, which is quite strong. Okay. What do they do, or how did they prove their theorem? They proved their theorem in a very different way that was before those results that I told you previously. In the previous result, the main approaches was trying to measure the resolvent of the operator, the growth of the resolvent when we approach to the spectrum. Here, they use what we would call a sort of unconventional functional calculus. They integrated the resolvent through a contour that cuts the spectrum. The spectrum, for technical reasons, like Xavier said, is very smooth here. It's that the closure of the lambda, but it can be very terrible. And they integrated the resolvent through special contours and provided some expression for formal operators in the bicommutant. Analyzed those operators in order to produce hyperinvariant subspaces. That was their approach. Clearly, here we have singular integrals because we're integrating through something which cuts the spectrum and unbounded. Anyway, a refinement of the results of Foyas, Janko, and Pearcey was done by Fang and Xiang a few years after, and they proved that if the growth condition of the coefficients of u and b are in L1, then you have also hyperinvariant subspaces. So if I take my naive picture, now we're covering the whole blue square. But still there are some room left, right? Okay. So in a first step with a former PhD student, Javier González Doña, we proved that if either the coefficients of u are in L1 or the coefficients of b are in L1, you can always produce hyperinvariant subspaces. So we were covering, okay, of course, in this picture, once you cover one area, everything inside is covered, right? So we were covering those purple square and also the previous one. Our approach was completely different. We were not using this unconventional calculus. Somehow it was very naive, I must say, but maybe we were lucky, I don't know. But we were able, okay, I wanted to put the hands on the subspaces. I mean, I wanted something like Berlin theorem. I wanted a specific handmade subspaces, and that provided us a few insights that allows us to extend the results in this first. Okay, after that, we were able to go a bit further with some techniques involving quasi-similarity and some operator theory techniques, let's say, we were able to say that if the coefficients of U, I need to assume that they are not zero. If they're zero, or the coefficients of B are zero, then it has non-trivial closed invariant subspaces for simple reasons. I will tell you after that. But if they are not zero, if any of the alpha n's or beta n's are zero, then the rank 1 perturbation has non-trivial closed invariant subspace, provided this growth, this series, is convergent. And if I make this naive picture, we're covering almost the right upper square. Almost. I mean, this is a picture, of course. If you want to provide several papers, you can put lock there, and the same techniques work. So, of course, there can be a machinery, but probably not that interesting. Anyway, so we don't know what happens in the general case. I mean, we don't know how to cover, in some sense, the border of that line. In other words, what happens for just a standard rank 1 perturbation of diagonal operators. So let me tell you about straightforward cases, because that gives you a reduction on which operators should be studied. And if there exists, this is what I was telling you before, if there exists a coefficient of U or V which is zero, then what happens is that either T or T star has an eigenvalue, and then we're done. Okay, it has invariant subspaces, non-trivial hyperinvariant subspaces. If any of the elements that I write down in the diagonal of the operator has multiplicity bigger than 1, strictly bigger than 1, I mean, has multiplicity 2 or bigger, then what happens is that such an value is an eigenvalue of T, and then we are also done. And if the set of accumulation points of the sequence in the diagonal is more than a point, it's more than a singleton, then what happens is that you can construct a compact operator that commutes with this operator, and then we are also done because of Lomonosov theorem. So basically, in all these cases, we know what happens. So what we're going to assume is that the coefficients alpha n and beta n are not zero. We're going to assume that the sequence that you write down in the diagonal are just of multiplicity 1, and they have a set of accumulation points more than a point. For instance, my favorite set of lambda n is just a dense set in the unit disk. But this is because the unit disk is my favorite set of the plane, but closed unit disk. Anyway, so we're going to call these classes of operator RO. This was introduced by Foyas, Janko, and Piercy. I don't know why they call it RO. I guess the rest of operators, the ones that are interested to study, but really I don't know where the name comes from. I assume that. So those are the operators with, in principle, don't know what happens with their invariant subspaces. And which was our strategy? As I said, our strategy was trying to construct explicitly invariant subspaces. And for that, we made use of local spectral theory. And this is not a crash course, it's even just one slide course about local spectral theory. Local spectral theory gives you particular invariant subspaces. Those are spectral subspaces. Let me tell you what it means in a couple of lines. Okay, to know about the local spectral theory, we need to understand first thing is the single value extension property for an operator. So if we have a Banach space, we will say, and a linear bounded operator in that space, we will say it has the single value extension property. If for every connecting open set that we take in the complex plane and every function f from G to X is a vector valued, right? If T minus lambda I, f of lambda is 0, then that means that f must be vanishing on G. This is a property for operators that allows us to define what is the local spectrum. The local spectrum is something a little bit more subtle, a little bit much more subtle than the spectrum. It depends on the vector, and is defined. I fix a vector x. The local spectrum is just the complement of the set of all those complex numbers, such that there exists an open neighborhood and an analytic function defined on that neighborhood, such that I can invert locally the operator t minus set I acting on x. I can invert for every set in that open U lambda. So basically, this is telling us, in some little words, is that locally we are able to invert the operator. Maybe the operator is not invertible at all, because, but I can invert on some particular vectors of the space. So the local spectrum, clearly, is always contained in the spectrum. It's a compact subset, but it can be empty. Like, we know that the spectrum of an operator is never empty, right? It's a compact. Anyway, so this is how we approach the problem, because what happens is that if you have a subset of the complex plane, and I look at the space of the vectors in the Banach space such that its local spectrum is contained in that subset, this is a linear manifold, which is indeed hyper-invariant. It's invariant under everything that commutes with t. That's the key point. Unfortunately, it's not closed, even when the subset that you take, even when omega is closed. If that happens for every omega, then the operator is said to have the Dunford property. Okay? So this can be zero. Just a linear manifold can be zero. It can be dense. We don't know if it is closed. Sometimes it's closed. It depends on. So what we did was trying to understand what happens with these spectral subspaces. We know how to compute spectral subspaces for some particular operator. So that was our approach. So how did we do that? And here is where complex analysis and the old style of Sasha and Nikolsky came out, in some sense, into the scene. How did we do that? We defined a function which is associated to this rank 1 perturbation of the diagonal operator. This is a Borel series. Recall, alpha n are the coefficients of U, beta n's are the coefficients of B, and then the lambda n's are just the elements in the diagonal. This is a Borel series. And a Borel, what I found, and I was not an expert on this, is that this has a very interesting history and very, very nice results. If you have an L1, I'm going to make a sort of detour in order to give you how we approach the problem, and I will wave my hands at some point. But anyway, let me go through this. So if you have a bounded sequence, distant point, right, and A is just the closure of that sequence, and you take any Cm in little L1, then you can consider the function that series, which is the Borel series, and of course, it's very easy to prove that the series converge uniformly on compactors in the complement of A, and it defines an analytic function which extends metamorphically to a neighborhood of each isolated point of lambda n. And as I said, this has a rich history, and there were basically two main questions to understand since Borel. Which functions are represented by Borel series, and when you have unicity, I mean, when it is represented in a unique way. And clearly, this interesting situation is when you have holes. I mean, imagine you have several holes, and your sequence lambda n is in the domain, and what you want to understand is what happens in each of the holes for this series. And if it can be zero in one hole, so that means that represented zero as a series. That was a question raised by Borel, and there was a result by Walsh that says that if the Cn decreases too fast, then this is not possible. Okay. What is the relation between the Borel series in the different components of the complement? But there are many other constructions, one by Wolf using the harmonic functions. He constructed a Borel series that is 0 in the unit disk, and all the lambda ends are like in an annulus. And there are further constructions by Denjoy, Berlin, Lenteva, and these series were summing up 0. What happens with the uniqueness result? Okay, for uniqueness result, there are theorems by Borel, Carleman, Gonchard, Poincaré, and more recently by Makarov and Nicolai. And one of the PhD theses that Nicolai was the advisor, it took us a while to get it from Bordeaux, and that was made by Sibilev. And how is this playing a role in operator theory? Okay, here Sarrazin is the master in some sense, and he was telling us that, or there is a theorem by him, maybe said, better said, that this Borel series sum up 0 for a set which is far away from the lambda end, and for some non-trivial Cn in little L1, if and only if we are able to find an invariant subspace for D lambda, I mean for the diagonal operator, which is not invariant under its adjoint. That means there exists an invariant subspace which is not reducing. Anyway, that was the connection, and this is what we were using in order to characterize some spectral subspaces for this rank 1 perturbation of a diagonal operator. So I will give you, this is the technical result. The proof is long, around 10 pages, and I will give you the statement. I'm measuring, I have no blackboard, but I'm measuring those points that are cut. The lambda ends are NA, are the integers, the positive integers, such that lambda n are in A, and the spectrum of d lambda, and this is a notation for the standard function that basically is like the derivative. So this is the technical result, and let me point out, I don't pretend that this is, I'm going to tell you about a couple of things about this result, I guess. That's the, I stated for rank 1 perturbation. Later we will see what happens with the final Elemeni, but imagine that you have an operator which is in RO, those that we don't want, those that we do want to understand. Okay? And then assume that it has the single value extension property. If the point spectrum of T and T star is empty, which I can assume, then it has the single value extension property. That's not a problem. And the spectrum is connected. Otherwise, I can construct invariant subspaces. And assume that I have a closed subspace that cuts the spectrum. Okay, then I want to understand the spectral subspace associated to that closed subspace. I mean, I want to understand those vectors such that the local spectrum of that vector is contained in that closed subspace. And that happens if and only if a vector is in this spectral subspace, if and only if there exists a holomorphic map, Gx, in the complement of F, such that if these are the coefficients of the vector, I'm interpolating every coefficient with that holomorphic map. This must be a vector-valued holomorphic function. But the most important thing is that I need to have a functional equation involving the Borel series and somehow the derivative of this function Gx. So this is quite important for every set in the complement. Regarding, as I said, this is the technical result, but this does not depend on the summability condition. So basically, our approach was, okay, if we are able to prove that the spectral subspaces are non-zero by this, by constructing specific elements, and non-dense, then we're done. And this is what we did. Okay, that says that sometimes I can find out which are the explicit functions. But if these are the spectrum, for technical reasons very smooth, but you can assume anything in that sense. So what if I take this particular two curves, I want the spectral subspace which is contained in the closed set determined by this curve. That's F1. I want the spectral subspace, which is such that is determined for this closed set, F2. And now what happens is that those two spectral subspaces, one is contained in the orthocomplement of the other. So that means that if I'm able to construct a point, which is what the characterization gave me, that means that these are not going to be dense. So they are non-zero, they are not dense, so we're done. And this is how we prove it. Where is the summability condition used in order to prove that I have a non-zero vector inside that subspace? So I need to get that summability condition. So I don't know how much oh, okay, all right, good. Actually, this is a way, we put the hands on the subspaces. And because of that, we were able even to decide how to produce infinitely many invariant subspaces, for those that we didn't know. And we were even trying to describe, in some sense, those. And this is a concept introduced by Foyas in the 60s, and is related to spectral operators. Those are operators very similar to normal ones. And these are decomposable operators. What is a decomposable operator? A decomposable operator, or an operator is called decomposable, if for every open cover that you take of C or of the spectrum, you're always able to find invariant subspaces, Y and Z, such that the X is the sum. It does not need to be even direct sum. Such that the spectrum of G restricted to Y is contained in one of the elements of the cover, and the spectrum of G restricted to Z is contained in the other element of the cover. So if this is U, and this is V, and the spectrum of my operator is just the red circle, then what happens is that the spectrum on each of I find two invariant subspaces, Y and Z, such that the spectrum is contained in each of the. So as you may imagine, okay, normal operators are decomposable operators. As you may imagine, it has a rich lattice of invariant subspaces, as many as any cover I can make, basically, of the spectrum. Which are decomposable operators? Unitary operators are decomposable. Normal operators, compact operators, operators with totally disconnected spectrum. For those, I can give a rich lattice of invariant subspaces. What happens with compact perturbation of normal operator? There was a previous result by Rajalabipur and Rajavi that says that, okay, if the spectrum of N is contained in a C2 curve, they were measuring growth conditions, so they need some sort of smoothness, then T is decomposable if and only if the spectrum does not fill the interior of the curve. Here, K had to be in a Chatten class. But not every compact perturbation of a normal operator, even contained in a very nice curve, is decomposable, and there was an example of Herrero in the 70s. Okay, what we were able to prove is that under the conditions that we had, under the summability condition that we know that there exists invariant subspaces, the operator is indeed decomposable. So it has no, we were lucky in some sense in order to produce invariant subspaces, but somehow they were there, and they were infinitely many. And so if I take, again, my naive picture, if the point spectrum of T union the point spectrum of T star is at most countable, if it is empty, which is the case when we want to understand invariant subspaces, those operators has lots of invariant subspaces. Actually, they are decomposable. We don't know what happens on the boundary. And once again, I say there is some singular integrals behind those stuff. I must say that there are some works from Foyas, Janko, and Piercy, Fang and Xia again, about decomposability, Chevron, Albrecht and Chevron, and more recently trying to understand this sort of idea of decomposability They are different from our approaches, and they are not giving the same results, but in any case, they're trying to make spectral cuts in these cases. In order to prove that this is a decomposable operator, what we did was trying to produce a rich family, what we call a spectral idempotents. What is an spectral idempotent? I will give you very basic definition. I know this is not the right time to give a definition, but the spectral idempotent is just an operator in the bicommutant such that the range of that operator is a spectral subspace associated to one piece of the spectrum. When you have a rich family of spectral idempotents, you can provide decomposability, and this is what we did, and that was coming from these spectral subspaces that I showed you. Okay, this is what I said. You make for one rank perturbation with lots of work, but the same ideas, you make it for finally many. I mean, find a rank perturbation of a diagonal operator, and you get the same. Of course, it's more involved. You have matrices. You need to take care of those matrices, but still, there is no special idea there in some sense. What happens if instead of finite rank, we go for infinite rank? And here, I must say this is a nightmare, or at least it was a nightmare for us. We don't know what happens with infinite rank perturbation of normal operator. This is not known. Even for the diagonalizable ones, we don't know from the standpoint of view of invariant subspaces. We don't know this. Come on. How can we solve the invariant subspace problem, right? Even for Schatten class of diagonalizable normal operators. As I said, there are still also lots of work, lots of authors trying to understand what happens in this context. And clearly, our goal was, okay, if we can prove for some subclasses that they do have invariant subspaces, can we say something about their invariant subspaces? Can we have some sort of decomposability? And with González Doña, okay, what we were under the condition that we had for just rank 1, I mean this log condition, when that is happening, when you have an infinite rank perturbation, that means that this is a trace class operator. So I'm not proving everything for trace class, I'm just proving that for those trace class operators such that this condition is holding, then the operator has non-trivial closed hyperinvariant subspaces, and indeed, it's also decomposable. And now the technique had to do differently, and of course the finite rank perturbations was not helping us because that depends pretty much on the finite rank somehow, and this is infinite rank. The idea was extending this spectral idempotence and construct a rich family. And there was, of course, an obstruction. At least we were not able to make it with Fredholm theory for finite dimensional operators, so we need to go through another techniques, and we were able to find out some operator that makes a sort of invertibility that plays a role with the finite rank. But that's the most technical part, so let me skip it. One again, there is this unconventional functional calculus involved in some sense. So there were two goals for today. One is I have a diagonal operator, no matter the spectrum, and I make a compact perturbation, finite rank 1, what happens when the invariant subspace. Now let me go for the second goal very briefly. Now I have a safe adjoint operator. Very nice. Its spectrum is contained in the line. If you were lost, this is the time to catch up again, because somehow, and I'm going to make a compact perturbation. But clearly, now, if it is finite rank, we are solved. I mean, this is the old results by Kitano. If it is infinite rank, but it is in the Schatten class, we are done. So we're taking a compact perturbation of a subjoint, but no regularity on the singular values. What can we say? Here we don't know the answer. We don't know if it has invariant subspaces or not. And of course, if you want to provide invariant subspaces, the only, you can try to understand universal operators in the sense of rota, but this is not very promising, or at least we were not making any success of this in this context. So let us come back to the old ideas of Aronsans and Smith and the quasi-triangular context, right? This is a quasi-triangular operator, and we have a sequence of almost invariant subspaces, right? Those PM. And then we study what Aronsans and Smith did in their paper for compact operator. I mean, this Aronsans and Smith procedure. You take the sequence of orthogonal projections, PM, and then you're able to produce another sequence of projections, final rank, the QNs. They are not going to converge strongly in the operator theory to the identity. What I'm going to do is that they're going to converge to an operator Q, which is not the A0 and is not the identity. It's between C, it's a positive contraction, but it's not the 0 and it's not the identity. The price I pay is that this new sequence, Qn or Qnk, it only converges in the weak operator topology. That's the price I pay. The limit is just Q, but this is the price I pay. And why is this interesting? I mean, the QNs also satisfy this approximately finite. The number goes to 0, right? What is the advantage? Okay, you pay a price, now they don't converge to the identity, they converge to this positive contraction. Okay, if the kernel of that Q is not 0, we're done. We have an invariant subspace for T. And if the kernel of, of I minus Q is not 0, then we're done also. So if the point spectrum of Q has 0 on 1, then we're done. So this is something that we get for free. So the idea is trying to understand this Q that appears in this process. And that was done in some sense for, by Foyas, Hamid, Onika, and Piercy in 2009, because what they say is that take an operator T and decompose like its real part and imaginary part. Okay, so I'm going to assume that the imaginary part is compact. This is a compact perturbation of a subjoint operator. Okay, if the imaginary part is compact and positive, and this Q has point spectrum that meets the unit interval, 0, 1, open, then you win. It has a hyperinvariant subspace. Actually, it has a reducing subspace, which is a lot. It's a subspace which is invariant under the operator and its adjoint. What they prove is that if I take the eigenvector associated to the eigenvalue of Q, that's a reducing subspace for T, which is contained in the kernel of the imaginary. If you may imagine, if you see the theorem by them, I mark it in red, they ask two things. What happens if the imaginary part is not positive? And what happens if I cannot find, of course, point spectrum of Q? And these are the questions. What is the role of the imaginary part? There are several papers by Makarov and Carlton trying to understand also the imaginary part of this. What happens, can I get something in this case? If you analyze the proof carefully, the point, if you know a little bit about Aronsans and Smith and go through this, what we found is that the key role of the whole story was played by I minus Q, TQ being self-adjoint. So what we did was introducing a class of the class of operator associated to T, all those linear bounded operators such that it makes I minus Q, TQ, self-adjoint. Okay, that's the class. Of course, it contains 0, it contains the identity. And in a joint work with my current PhD student, we were trying to address the questions by Follas, Omid, Anika, and Piercy. We understood when you have reducing subspaces, that's the theorem. And actually, what we prove is just the converse of the result by Follas, Omid, Anika, and Piercy in the following way. If you have lambda, T, a linear bounded operator, and a value lambda different from 0 and 1, T has non-trivial reducing subspace, which is contained in the kernel of the imaginary of T, which is what they get, then there must exist a self-adjoint Q in this class, ST, such that lambda has to be an eigenvalue for Q, which is what they use in order to prove their theorem. So the converse, which is a little bit long, is also true. So indeed, in order to tell you what is the role of the imaginary part being positive, the answer, roughly speaking, is no one. Actually, you can even consider the modulus of the operator and get basically the same result with the different techniques. We were analyzing that class. I called the Aronson and Smith class, and several properties. And with that, this is a class. Basically, it tells you, give me any operator. It doesn't depend if it comes from the Aronson-Smith scheme or not. What we were able to show is that if this is a self-adjoint operator that belongs to 0 and 1, then T always have a non-trivial closed real invariant subspace. So this is the closer thing to the invariant subspace problem. Actually, this is very close to a previous result of Lomonosov, which is not the Lomonosov theorem that everybody knows. Lomonosov proved that if an operator has a compact imaginary part, it always has a real invariant subspaces. And that comes as a corollary of in this result, because if you have an operator with compact imaginary part, there is a self-adjoint operator in the class ST. And if this is the case, T has a real invariant subspace. To end up my talk, I guess the most significant consequence, at least from my perspective, when we analyzed this class and trying to understand how it was playing a role in order to understand the compact perturbation of self-adjoint operator, is the following equivalence to the invariant subspace problem. Every linear bounded operator on a separable infinite dimensional complex Hilbert space has a non-trivial closed invariant subspace if and only if, for every linear operator that I take T, I'm able to find a self-adjoint operator Q in the class ST. Recall this, I wrote it there for you, such that it's not 0 and it's not the identity. If I find out any self-adjoint for that operator, somehow, the operator T has non-trivial closed invariant subspace. It's not coming for Q, but I can construct one of these invariant subspace for it. So I guess the basic question that Buddha allows us to understand further the invariant subspace problem is what happens for the invariant subspaces for compact perturbation of normal operators. If we're able to solve that, for instance, we would solve the invariant subspaces for hyponormal operators that we don't know, and even more than that. So this is the end. I think, the references have been given there, but I think, Sasha, happy birthday, and thank you for your attention.
Thank you very much for this beautiful talk of invariant subspace problem. And now the time for questions.
I can ask you,
paper with maybe some error
Yes.
in this paper where he claims that there is always the invariant subspaces, and then there was a correction also published that for compact one-sided perturbation his proof goes on. Whether this correction is verified or not,
No, it's not. That is not true. Also, I mean, there was this correction, and the basic story is that for compact perturbations, even for self-adjoint operator, we don't know. I mean, and his proof is not working, unfortunately.
No, but it's not all compact perturbation, but one-sided. So, say dissipative or contractive, if you think about the unitary operators instead of self-adjoint. It's the same, yeah? It's not clear, yeah?
It's not clear to me. I don't know what you exactly... Okay, what I know is that there is the branch paper, which actually James Roniak, we sent this also to James Roniak. There is the branch paper that when you have invariant subspaces which is not holding, he was able to construct some invariant subspaces using Weierstrass theorem, approximation Weierstrass theorem, and I think this is the one you're mentioning. And from my perspective, and as far as I knew from Jim, is that it's not working either.
Yeah. So, say for the Schatten class perturbation, so the theorem holds.
Yeah.
And it is with the functional calculus.
Exactly.
Techniques.
Exactly.
Whether, say, the more stronger functional calculi as Dynkin asymptotically holomorphic functional calculus is employed to get something new or not?
I don't think this is employed to get some improvement, but okay. If you have a self-adjoint operator, a compact operator, even in trace, which is not in trace class. If it is in trace class, you have this growth condition on the resolvent that allows you to construct invariant subspaces. Yeah. Basically, as I said, right? But this is a growth condition on the resolvent. This functional calculus that somehow was used in the work of Foyas, Janko, and Percy. Go to that. Yeah, somehow this functional calculus that they were, instead of looking at the growth of the resolvent, what they were doing was trying to integrate the resolvent through these contours and produce a formal operator which is going to be in the bicommutant. That's how they proceeded. It's a little bit tricky. Actually, this is a very naive way to see this. But this 2/3 is an integrability condition that they were using. If you're considering the integral between 0 and 1 of 1/x to power p, this is an integrability condition that they needed to make that integral work. And the result by Fang and Xia, they're able to make till 1 because they were able to make that integrability condition push further. It is the same idea, but still. But if you don't have that integrability condition, you're not, at least we didn't succeed, or they didn't succeed either, to produce the invariant subspaces with that techniques that comes from the functional calculus. So somehow our approach was, I wanted some sort of Berlin theorem for the cases we knew. And then we find out that you are able to produce these spectral subspaces. But you know that the spectral subspaces for the Schiff operator are basically trivial, right? So.
Thank you.
More ones? A short question. In the study of invariant subspaces, there is direction, and people consider the predual subspace to
the predual, yeah. Mm-hmm.
And prove that every functional is generated by rank 1 operator. So did someone checked in the setting of Lomonosov theorem, does operator has this property or not?
You mean in the setting of the Lomonosov theorem,
Yeah.
the one that proved that every compact operator has non-trivial closed hyperinverse? I know that the techniques of predual, the predual techniques were used by Bercovici pretty much, and they were trying to understand what happens with even with contractions. I guess maybe this is what you wanted to mean, but no, as far as I know, no.
Okay, thank you.
Okay, so I was informed that we have short on time, so this was the last question. So let's thank the speaker once again.
Thank you.
Да, кто-то придет. So let's start the afternoon session of this day. And the first speaker is Professor Petr Juditsky of Linz University. He will speak about point spectrum of the Jacobi matrices generated by iteration of quadratic polynomials, as written on the screen. The close friend of Sasha. Okay.
Many thanks to organizers for their great job. I will speak first about almost periodic Jacobi matrices generally, and definition is as follows. We consider sequence B, it's called almost periodic if the system of shifts of this sequence is a precompact set in L infinity. Such set has the following descriptions. There exists a compact abelian group G, a fixed element omega of this group, and continuous function B on G, such that for any alpha, we form sequence. We start with value alpha, and then moving in the direction omega in positive and negative direction by step omega. And as a result, we obtain almost periodic sequence, and vice versa. Any almost periodic sequence possesses this kind of representation. For example, consider as a group one-dimensional torus. B of alpha is cosine with a certain amplitude factor A, and then we form the following sequence. As soon as omega is rational, then of course sequence is periodic. Otherwise, this is a nice example of almost periodic sequence. Jacobi matrices are the free diagonal matrices. They act on the standard basis En in the space L2 according to this rule. We will consider bounded operator. For this reason, A and B are coefficient sequences belongs to L infinity. We will consider self-adjoint operators. For this reason, we can normalize An to be positive, and Bn should be real. J is almost periodic Jacobi matrix if the coefficients of sequences A and B are almost periodic. In other words, we consider all possible shifts of the given matrix J, and this collection of Jacobi matrices is a precompact in the operator topology. In the spectral theory, there is nothing more simple than spectral theory of self-adjoint Jacobi matrices. On the other hand, спектральная теория почти периодических матриц также неисчерпаема, как и атом. In English, this is probably spectral theory of almost periodic matrices is like President Trump. It never fails to surprise you. First, we will discuss Jacobi matrices in the case that there is absolutely continuous spectrum of Jacobi matrix. Metrics are related to measures, and if measure is absolutely continuous, then we say that operator has absolutely continuous spectrum. The following result, Christian Rebling find fundamental result, which is as follows. We consider one-sided Jacobi matrix J plus tilde, and then we consider all possible so-called right limits. So for any sequence Nj, there exists limit along with subsequence A epsilon k plus Nj and B tilde k plus Nj as Nj tends to infinity. And in this way, this is for each fixed k. In this way, we obtain two-sided Jacobi matrix, because here we can use, of course, k as positive as a negative. The set of right limit is non-empty. The theorem deals with the following fact. Assume that the absolutely continuous spectrum of matrix J plus, which we denote by E, and we assume that E is non-empty, that is, the length of the set E is positive. Now, we consider any reflectionless Jacobi matrix, then, we consider any limit point J of I, we consider any diagonal element of this matrix, and then the claim is that boundary value of argument of RK, this is function with positive imaginary part, on the set E for almost every x in E is pi over 2. So always just pi over 2. This means that how important this class of the property is called reflectionless, and this shows how important the class of reflectionless matrix. Any matrix with absolutely continuous spectrum, in a certain sense, is just a perturbation of reflectionless matrix. Well, we introduce a collection for given set E. We introduce of positive length. We introduce a collection of reflectionless matrix with the given spectrum and denote this by J of E. Catani last had the idea that as soon as E is positive and we consider reflectionless matrices, then all of them are almost periodic. Together with Misha Sodin, we partially confirmed this idea. Indeed, as soon as E is homogeneous set, then indeed all reflectionless matrices are almost periodic. But with Sasha Wolberg, we found the following, that in fact there exists purely analytic property of the domain omega C without E. This is purely analytic property of the domain, such that as soon as this property for the domain holds, then indeed all the reflectionless matrices are almost periodic. But in generic case, as soon as DST fails, then no one of such operator is almost periodic. Sasha called this, we built a small theory. Now we turn to the case then the length of the spectrum is 0. In this case, we do not have any small theory, but instead we have beautiful examples. We study spectral property of Jacobi matrices from two sides. From one side, which is when we have given operator and we study spectral property, this is so-called direct approach. And inverse approach deals with the case that we start with some spectral property of operator, and then we build operator and try to prove this or that property. Among operator examples from the direct side, the best known examples, so-called almost Mathieu operator. We assume that AN coefficients are 1, BN coefficients are given by cosine function, and case A is equal to 2 is called critical. In this case, spectrum of such operator is of Lebesgue measure 0. Arthur Avila proved that as soon as omega in this formula and initial alpha are not rationally related precisely in this sense, then the operator has no eigenvalues. So the spectrum should be singular continuous. And comparably recently, Lana Zhytomyrskaya proved that for all alpha, the spectrum, there are no eigenvalues. And this was proven of the conjecture of Barry Simon of the year 1982. Well, we are working with inverse spectral approach, and in this approach, the main example deals with iteration of quadratic polynomials. We consider quadratic polynomial z square minus lambda for lambda greater than 2. This is so-called expanding polynomial. And using this polynomial, you can build so-called Julia set of this polynomial. You can build it as intersection of inverse iterate, starting from the interval minus xi xi, the xi is fixed point of the quadratic polynomial. You get, as inverse iterate, you get first 2 interval and 4 interval, so like Cantor set procedure. And intersection of this En is a so-called Julia set of the given polynomial. Or another way, which we like in Kharkov, to represent spectral set in terms of so-called conformal mapping on so-called comb domain. There is such nice comb. This is half street in which we cut first in the middle something of the height a over 2, when two cuts of the height a over 4, and so on. And then we make conformal mapping of the upper half plane to this domain. This normalization, theta of infinity is infinity, theta of minus psi is -1, theta of psi is 0, and preimage of the base is exactly Julia's set related to quadratic polynomial. Of course, between values a and lambda, there is one-to-one correspondence. And then the Lebesgue measure on the base of this comb corresponds to harmonic measure on the set E with respect to infinity in the complement to the Julia set. Another way, mu of y minus mu of x is theta of y minus theta of x. In the year 1982, two groups of mathematicians, Belisard, Basis, Musai, Barnsley, Geronimo, Harrington, proved the following fact. Let lambda be greater than 3. I'd like to mention that expanding polynomial corresponds to value of parameter lambda greater than 2. But let lambda be greater than 3. And then we consider orthogonal polynomial with respect to measure mu. Once again, this is harmonic measure with respect to infinity on the Julia set. And then we orthogonalize polynomials with respect to this measure. We get a sequence of orthogonal polynomial pk. And of course, they are related by free term relation, and this generates a Jacobi matrix. Coefficients bk are 0 because measure is symmetric, and we have these coefficients ak. The lemma states that the following inequality holds uniformly in k and s. What does it mean? They have coefficients ak. We take part of this coefficient of the between 1 and 2n, and then just extend this coefficient periodically. And when we compare this periodical system of coefficient with initial, and they are distance less than epsilon, so that n tends to infinity, we have the coefficients are uniformly approximated by periodic sequences. In this sense, coefficients are called limit periodic, and they prove that we start with the measure which is evidently singular continuous. We build certain Jacobi matrix which is limit periodic, and as a result we obtain limit periodic Jacobi matrix with singular continuous spectrum. Marchenko asked that if you have something which is limit periodic, it should have natural extension on negative indexes. So there should be not only J plus, but matrix J minus, and he asked what kind of spectrum is related to this J minus. I would say in advance that in fact we can consider not only this matrix consisting of G plus and G minus, but also all possible shift and closure of this shift. And since the result should be almost periodic, therefore there should exist abelian group which parameterize this collection of almost periodic. And in this case, this abelian group is a collection of two adic numbers. I recall that this is a closure of integer number in the topology which is given here. Now, due to the main property of coefficients of this matrix, actually A kappa n is a fundamental sequence, and therefore you can extend your coefficients on any kappa which belongs to Z2. We obtain function A on the Z2 group. And now we have, of course, this not only for positive but for negative coefficients, and therefore in this way we can construct J minus. With Misha Sodin we prove that this J minus is also operator with singular measure, with singular measure without P-point spectrum. Of course, there was a very interesting question: what about lambda greater than 2? That could we prove limit periodic property for any quadratic expanding polynomials? And there was a lot of efforts related to proving, and the question is still open. The best what we were able to do with Sasha to show that the same is related to any, not only to quadratic polynomial, but to any expanding polynomial with sufficiently big critical values, also related to such object operators are limit periodic. Okay, so now we have not only one Jacobi matrix J of 0, but also the thing which is called Hull, collection of all shifts and closure of these shifts. And we denote this by J of kappa. Note that for kappa 0 or any integer, the matrix split too emotional. Okay. Is split into orthogonal Jacobi matrices. In general, as soon as kappa is the 2 without without the integer numbers, no coefficients equals 0, so we indeed have two-sided Jacobi matrix, which is not orthogonal sum of two one-sided Jacobi matrices. And the question is it true that these matrices are also has no eigenvalues, that is related spectrum is singular continuous? And together with Benjamin Eichinger and Milivoj Lukic, we prove that indeed no eigenvalues for all kappa. I have a question: what about unitary equivalence of this J of kappa? Because in the case when the spectrum was absolutely continuous, we indeed were able to prove that all of them are unitary equivalent. As soon as this would be unitary equivalent, of course, we would get immediately that if one matrix has no eigenvalues, then any other matrix has no eigenvalues. However, I actually do not believe that such matrices are unitary equivalent, which is different from the case of absolutely continuous spectrum. The main tool was a so-called real version of Perron-Frobenius theorem. This is a very strong tool from the theory from dynamical system. I will recall this from Perron-Frobenius theorem, real version of Perron-Frobenius theorem. Let phi be a Hölder function on the Julia set E. To this weight we associate the following operator acting on the continuous function on E. The claim is that spectral radius of this operator is an isolated simple eigenvalue. For this reason, the following limit, 1 over rho n and so on any function f tends to the following expression, so it tends to operator of rank 1. Here h is an eigenfunction of the operator, and nu is an eigenmeasure for the conjugated operator. The reason why it's called version of Perron-Frobenius that here such operator all continuous function maps to, all positive function maps to positive function. And now if we consider two operators, one is the trivial weight, L0 and 1 with the weight of the form 1 over t prime square, t is our polynomial, then eigenmeasure related to L0 conjugated is exactly our harmonic measure on the Julia set mu, and with respect to extension to the negative axis, the spectral measure related to J minus is exactly eigenmeasure of the operator L2 star. No, it's known in the dynamical system that both measures are singular continuous, so the matrix with J minus J plus is has singular continuous spectrum. Now, if we consider any arbitrary element of the hull, the spectral characteristic already is not a scalar measure, but two-sided Jacobian, but 2 times 2 matrix measure. So if we want to continue in the same way, we need somehow to generalize idea of real operator to the matrix case. We know that sometimes generalization to matrix K is simple. We know that sometimes generalization to matrix K is very non-simple. In fact, so the weight in this case definitely should look like this, multiplication by weight function P and P conjugated, because such operator X maps non-negative matrix function to non-negative matrix function. And conjugation operator, clear how it should be defined. But at the moment I don't know the theory which is generalization of real theorem to the matrix case. Moreover, in our case, we will need not just to take power of some fixed real operator, but we need to multiply real operator related to different weights. In particular, as soon as kappa is even, the matrix which form real operator is lower triangular. As soon as epsilon is kappa is odd, the matrix is upper triangular. What looks nice, the determinant of weight matrices is something which is nice. Maybe if we would have a general theory, this helps a lot. Main algebraic lemma is indeed, besides that we can add two-adic numbers, we can multiply two-adic numbers, we can shift two-adic numbers. So there is operation of shift on two-adic numbers. And this operation of shift indeed generates action of the real operator on with the weight which was shown before on spectral measures associated to given Jacobi matrices. And as in the case of almost Mathieu operator, we also have two cases. One case is very, very simple. One case is not that simple. All set Z2 can be split in two subsets, G delta and F sigma. And for G delta, that is for practically all, the proof is very simple. And for F sigma, the proof is not that simple. F sigma, this is a union of the sets Fn, and Fn is the following set. Consider, so in the representation of the two-adic number kappa, there should be no more one by one elements of the same element. So 0 could not be repeated more than n times, and 1 could not repeat than n times. So formally, if in the representation epsilon k is equal to epsilon k plus 1, epsilon to k plus n minus 1, then next epsilon should be different. So this is the set Fn, union of so this is nesting perfect sets, and union of these nesting perfect sets we denote by F sigma. So once again, in the case as kappa belongs to the complement to F sigma, to the set G delta, then the proof is comparably easy. And the idea of proof is the following, that if kappa belongs to G delta, it means that we should make arbitrary long sequences of zeros, let's say. And shifting in a suitable way from the given kappa on the certain subsequence, you will arrive to the sequence 0, 0, 0, 0, 0 as the limit after shift. So if kappa belongs to G delta, then there exists a sequence nj such that shift power n converges to 0 or to 1. And proof based on some the following observations, that if x0 is an eigenvalue of j kappa, then in this sequence I kappa, we choose a subsequence I kappa x0 such that trajectory of starting with x0 converges to some y0. And the claim is if x0 is eigenvalue of j kappa, then y0 is an eigenvalue of j0. But j0 has no eigenvalues. This is contradiction. And the proof is based on duality. This is complete proof. I will skip this proof. But instead, I'd like to explain why we were needed in this theorem that Jacobi matrix has no eigenvalues. This was related to such notion as universality. Now we can forget what was before. For a measure of orthogonality sigma, we consider orthogonal polynomials, and we form so-called Christoffel-Darboux kernels. This is expression of this type. And first physicists and then mathematicians noted that there exists a certain kind of universality. If you fix some psi star in the support of the measure, and you make rescaling of the Christoffel-Darboux kernel, the rescaling is given by limit shown here, when for suitable tau n tends to infinity as tau n tends to infinity as n tends to infinity, then in the limit you always obtain the same function, sine pi z minus w bar over pi z minus w. So rescaling of anything leads to something which is universal. And there was a kind of mystery why this happens. And finally, the problem was completely resolved by Eichinger, Lukic, and Harmonic. And the answer is quite understandable for us. To the measure sigma, you should put to correspondence its Cauchy transform. As soon as psi star is such that the limit of m sigma psi star, so Cauchy transform, plus a epsilon exists, and it is non-trivial, then at the point psi star, we have, related to the given measure, we have this universality statement. Moreover, this coefficient tau n can be written explicitly in terms of reproducing kernel. The coefficient eta is needed just to have sine pi and not psi pi eta. In principle, this is interesting how tau n depends of n, but this is a separate question. otherwise, this universality law is universal. Later on, Eichinger, Lukic, and Voracek start to work with the case which include endpoints of the gaps, like orthogonal polynomials in respect to the Jacobi weights. So in the end of the gap, psi is in end of the gap, and in the end of the gap, our measure sigma behave like x minus psi star with certain power alpha. And they also found the corresponding universality limits. And then after they found this and that, it's interesting what's going on in the case of fractal. So assuming that measure is supported on some set, which has infinitely many gaps, and these gaps accumulate to something, to some point, and what kind of universality we can expect in this case. So what we found with respect to this question? We can consider the standard counter set. The standard counter set you can build like inverse iteration for the function free absolute value of x minus 2. Or you can consider counter set related to quadratic polynomial. You can consider counter set related to any expanding polynomial. Anyway, as soon as we consider point psi star, which is periodic for the given dynamics, periodic means that certain iterate of n of psi is psi star, then associated measure, a Fourier transform associated measure, behave in the following way. It's also behave like y in the certain power beta, but instead to have a limit after cancelling of value when m tends to infinity. It approach to a certain multiplicatively periodic function. Multiplicatively periodic means that there exists rho such that omega of rho of z is omega of z. And our main theorem is the following, that if this condition holds, then after suitable rescaling, Christoffel-Darboux approach not to a certain fixed limit, but instead there exists one, like was in the case of sine pi z minus w, but there exists a family of reproducing kernels parameterized by a certain parameter s. With respect to this parameter s, we also have property multiplicatively periodicity, and such that this difference tends to 0. This is a common way to describe the asymptotics of an object which does not converge but asymptotically approach to some periodic or almost periodic. This was how Akiezer or Widom represented the result. And the limit corresponds to a self-similar canonical system and can be seen as a new type of universality class. Rn was universal, but assuming that Losha Poltoratsky is here, he would definitely ask, nevertheless, how Rn, which is scaling parameter, depends of n. And we can to answer to Alexei partially, at least in the case of quadratic polynomials, the answer looks like this. As soon as the answer looks like this. There exist two periodic functions, C of L, C of 2L is CL, such that as soon as nk over 2k tends to L, then our rescaling parameter Rnk divided by nk in the suitable power tends to C of L. What is 2? 2 is the degree of polynomial. And what is rho? Rho is a multiplicator at the point psi star. Okay, if you already lost my talk, this is a moment when you can switch again. So you can follow. I will tell story about chimeras according to Sasha Wolberg. I will define a class. This is 2 by 2 matrix functions. I will call the class PDB. A belongs to PDB if entries of these matrix functions are entire functions. The following expression related to A is non-negative. I will call this CD form related to A. And the determinant of A of Z is 1. The entries are real. This is equivalent by practical statement. Example. If we consider so-called transfer matrices generated by Jacobi matrix, they belongs to PDB class. If we consider transfer matrix related to the Schrödinger operator, this is free Schrödinger operator, you get matrix from PDB class. If you consider transfer matrices related to Dirac operator, simplest operator, syntax transfer matrix looks like this, they belongs to PDB class. What is essential to add that remark that a 2-2 entry of our CD form is nothing but Christoffel-Darboux kernel. So 2-2 entry of this 2 by 2 matrix is exactly 2 by 2 kernel. Vladimir Petrovich Potapov proved that for given A of Z in the class PDB, there exists a continuous chain of matrices of the PDB class, such that these matrices are monotonic with respect to parameter T, and the family starts with 1 and terminate at the given A of Z. There are at least 2 reasons for non-uniqueness of such chain. First of all, we have a free parameter, so making change of variable from T to S of T, you get also chain of the same kind. And another thing, there is so-called what I called gauge freedom. You can multiply your matrix from the right on any constant matrix of the same class. As a result, you will get the chain which, if U of 0 is 0 and U of T 0 and 1, you will get the matrix of this, you will get a chain with the same property. Continue borrowing terminology from quantum mechanics, we can say that CD kernel is observable. This is certain expression which is gauge independent. And another fundamental observable thing, which is the spectral matrix, the resolvent function. As soon as trace of CD kernel diverges, then we have so-called Weyl circles which shrinks to a point, and this W of Z actually does not depend on choice of the gauge. And the branches prove the theorem which is related to uniqueness of this matrix of PDB class. So if initial matrix is normalized to be A of 0 is 1, and all elements of the chain are also normalized to be 0 at point 1, this is I call the branch gauge. And the branch parameter satisfies the following equation, when in this case we have a uniqueness, and actually the chain can be restored as a solution of so-called canonical system in the branches gauge. So this is the following equation, H of T sometimes called as Hamiltonian, and condition on normalization condition, trace H of T is 1. So this is the form in which you can rewrite any canonical system. However, classical gauges looks quite different. Here, parameter is not, for Schrödinger operator, is not like in the de Branch case, and gauge de Branch condition doesn't hold. Transfer matrix for Dirac operator also has the same property. Nevertheless, if I will just multiply, the class of PDB is multiplicative. If I will multiply these two matrices and normalize them so that by constant matrix, so that matrix A at the origin is 0, I obtain in this way a certain transfer matrix of a certain canonical system. However, such product Sasha called chimera, which is creature, which is formed from something not natural. Chimeras can appear in a natural way, remark first. In fact, Crane's problem on extension of Hermite positive function can generate chimera, it seems, in a natural way. Another thing, chimeras can be useful as soon as you have a very nice conjecture. But this nice conjecture do not take into account that chimeras exist. And then, using chimera, you can disprove this very nice conjecture. For example, like Catani-Last conjecture, or conjecture that inverse scattering problem has a unique solution. So with building chimeras with Sasha, we spoil two nice ideas. Okay, what is indeed the right parameterization according to Dirac? It's easy to see that this is just exponential type of the family of matrix. What is the right parameter for Schrödinger operator? This is, from the point of view of analysis, this is exponential type of order 1/2. In principle, we can introduce more general thing, M-type. Let E star be a closed unbounded subset of R. Omega is a complement to this E star. Let M be the symmetric Martin function at infinity. Recall that this is a non-zero positive harmonic function in omega such that restriction on E star is 0, and this function is symmetric with respect to real axis. Now, if the entries of matrix A of Z, entries are entire functions, but being restriction to the omega, they are not necessarily of bounded characteristic in the domain. But if they are of bounded characteristic, then we can define in a natural way M-type of such matrix. So M-type can be related to any Martin function. With Sasha, we discussed this concept and provided some examples in this paper. Okay, so now I'm ready to go back to quadratic polynomial. I will consider my quadratic polynomial in a little bit different form. Modification is related that 0 now is fixed point. Parameter rho in the given case is just this multiplier derivative at the fixed point. Condition lambda greater than 3 corresponds to a little bit ugly condition minus rho greater than square root of 13 minus 1, but the right condition lambda greater than 2 corresponds to a nice condition minus rho greater than 2. Now let mu be the balanced measure on the Julia set. Let f of z be solution of the Poincare equation. In the vicinity of a fixed point, dynamical system is equivalent to multiplication by rho. This function f, which which conjugate action of polynomial t with multiplication by rho, in the case of polynomial can be extended to entire function, and we call this entire function Poincare function because it solves Poincare equation. Okay, and then using this Poincare function, we can push forward. Push back harmonic measure mu, balance measure mu, on the Julia set. In this way, we obtain measure on the unbounded set E star, which is full preimage of the set E under the action of Poincare function. The new function W of Z, as any function, can be generate a certain collection of a certain de Branches chain, which I denote by A of ZT. The claim is that M type of this matrix with respect to domain C without E star is well defined, and moreover that L of T is continuous and strictly monotonic. This means that instead of the branch parameter, we can parameterize our system by M type, and in this case, the formula for rescaling now has a very nice and very understandable form. So nothing except for the parameter rho, nothing except for the degree of polynomial 2 is needed to make a right rescaling. In this right rescaling, you has a limit which is parameterized by L type, M type. An essential ingredient of the proof, absence of eigenvalues of our Jacobi matrices J kappa for all kappa. So we found a very natural parameter how to parameterize this chain, but this is equation is where a natural gauge dealing with normalization of this family at infinity, similar to Dirac and Schrödinger cases. With respect to when we were discussing operators related to canonical system related to positive spectrum, with Bessonov, Roman Bessonov and Miroi Lukic, we were able to understand quite good how it looks like the systems. But once again, with respect to case where spectrum has measure 0, we do not have actually good theory related no to canonical system, no to Jacobi matrices, but nice and interesting examples. Thank you very much for the attention.
Many thanks for a beautiful talk, really inexhaustible as President Trump, it's your subject. So there are some questions or comments, please. Sasha, you have something to add? No? You are quoted very frequently, no? Okay?
Okay. It seems that the talk was good.
Yes. Yes.
Everything is clear.
So if not so, thank you very much once more, and we resume at 4 o'clock.
We are taking the conference photo basically right now. So in front of the entrance to the Academy building. Thank you.